So in this video, we will look at how to find the coefficients for the Fourier series. We know that signals can be represented by adding together sines and cosines of varying frequencies in order to synthesize any real periodic function of our choosing. But the key question is, how much of each frequency do we use in order to reconstruct or to synthesize our function of interest? And that's what we'll answer in this video. So there is the Fourier series. We're saying that on the left-hand side, that is our arbitrary real periodic function, f of t, and we're saying it's equal to some constant offset term, a0. That's effectively cos of 0 with some coefficient a0, plus a set of cosine terms of increasing frequencies from n equals 1 to infinity, so I'm showing just 3 of them here, plus a set of sine terms of increasing frequency from n equals 1 to infinity, and I'm showing sine 1, sine 2, sine 3, omega naught t, just by way of example here. You'll notice I've got a factor of 2 in the front of these two summations, and that'll become clear as to why that is as we go on in this video. So the focus then will be, how do we find a0, how do we find all the an's, and how do we find the bn terms for the sines, the coefficients rather. So to give the answer immediately, to find the coefficient, for example, any coefficient an, of any of the terms, then what we do is we take the periodic function of interest, so f of t, and then we multiply it by the term for which we wish to find the coefficient. So, and then integrate and normalize. So for example, if we wanted to find the coefficient for the term cos 1 omega naught t, in other words to find a1, then we take f of t, multiply it by cos 1 omega naught t, integrate over the period of the function, and then divide by that range of integration. So that is the answer for how we find any of the coefficients for any of the cosine terms. But of course, we want to know, does this work? Of course, it does work, but why does it work? So we'll now look into some examples to try and unpack this very key equation. So imagine we wanted to find a0, the coefficient for the constant offset term, the kind of cosine 0, which is equal to 1. What is the scaling factor, if you like, the coefficient a0 for that term? Well, following the methodology of the previous slide, we take our real periodic function, f of t, and we multiply it by the term for which we wish to find the coefficient. So if we're trying to find the coefficient of cos 0, the coefficient of 1, if you like, the constant term, then we take f of t, multiply it by that 1, and then we integrate it over the period of the function, and then divide by the range of that integration, and that will give us a0. And in fact, that's going to be equivalent, as you can hopefully see here, to taking the average value. It's like taking the function values f over a range of time values from minus t over 2 to plus t over 2. In other words, that's the range of the period of the function. Add those all together, and if we just added them together, then we'd just get obviously the total area under the function over the period. But by dividing by t, we're then getting the mean value of this term, which is just f of t. We're getting the mean value, and that will give us a0, and we'll see why that is now actually in this slide. So why does that work? Well, let's take a real close look. So we're saying that f of t, as with our earlier slide, we're saying it's equal to a summation of the constant offset term plus an infinite number of cosine terms plus an infinite number of sine terms. Okay, so that's what we're claiming f of t is. Now the point is that if we do this definite integral over any of these sine terms or cosine terms, when we evaluate a definite integral, we will always get a 0 result. Why is that? Well, take a look at this. It's maybe easier to look at the example of the sine function here. You can see that the sine function is as much positive as it is negative. So if I add up all the values along here, they're all positive. All the values along that second half there, they're all negative. And they're equal and opposite, such that when I do the summation, I get a net result of 0. Exactly the same is true for the second frequency for the sine terms and the third frequency, and all the way up to infinite number of frequencies for all of the sines. We get a 0 result when we do the definite integral. Likewise for the cosine terms, if we do a definite integral here, the function is as much positive as negative, as shown clearly in the example here for the first cosine frequency. It's also true for these other frequencies. It's just that we get a kind of a half part of the peak on the left and the right hand side, and so you can see that there are effectively as many positives as negatives, and when we do the definite integral, it still turns out to be exactly 0 when we go over the period of the function. However, look here at the a0 term, that flat constant offset term. If we integrate that, we will get a definite finite result from the integration, which in fact is just equal to the amount, the amplitude, if you like, of that constant offset that goes into making up f of t, assuming that f of t has a net offset term. It might not, it could be 0, and if that is 0, then this result would give 0 for a0. But assuming it's finite, then when we do this definite integral, then we will get, when we also divide by the range of integration to get that proper mean value, because otherwise we'll just be overestimating, because if you imagine that's like a0 all the way along, then if we keep adding the a0s together, and if we don't normalize, then we'll get some exaggerated value. So we must divide by the range of integration. So assuming that term is present in f of t, then it will come out from this integral, this definite integral. So that's just demonstrating what happens with just one of the cosine terms. You can just see explicitly, as I pointed out on the previous slide, it's a function that's as much positive as negative. So when we integrate that, and in fact when we integrate any of the cosine or sine terms, definite integral yields 0 result. So therefore, in that previous slide, that's why we get a0 as the outcome from that definite integral. So that's all very straightforward for the flat constant offset term, if you like, the coefficient of cos 0. What about a1? What about the coefficient for cos 1 omega naught t? So let's follow our same procedure. We start out with our real periodic function, f of t. We multiply it by the term for which we wish to find the coefficient. So if we're trying to find the coefficient a1, in other words, the coefficient of cos 1 omega naught t, we take that product, we integrate the product, okay, over the range, over the period of the function. So here I'm taking it from minus t over 2 to plus t over 2, and then we've got to normalize to avoid that exaggerated addition of too many components, and that will give us a1. Okay, let's see why that works by taking again another look graphically at what is going on there. Okay, so again, here's the expression you just saw on the previous slide, and remember that we are saying that f of t, this real periodic function, we're saying it's composed of a constant offset term and a whole set of cosine terms and a whole set of sine terms. Now though, we're multiplying it by the term for which we wish to find the coefficient. So we're trying to find the coefficient for cos 1 omega naught t, in other words a1. Okay, so I'm showing cos 1 omega naught t here. Okay, and now if I multiply this function by all of these, we will see quite an interesting result. Okay, let's take a look one step at a time. If I first of all multiply cos 1 omega naught t by this flat constant offset term, which we are assuming is present in f of t, then I'm going to get, of course, none other than a cosine function of frequency 1, which is as much positive as negative. And so that product of the flat constant offset with cos of 1, when I do a definite integral, it will give me 0 after integration. Okay, what about when I meet the term of interest, cos 1 omega naught t, which I'm assuming is present in f of t? If it's not there, then that would be 0. and this definite integral would be 0, which would be the correct answer for A1 then. If it's not present, it should be 0. Assuming it is present though, then if that's present in f of t, when I multiply f of t by cos 1 omega naught t, what will I get? I'll get cos times cos, which is cosine squared, which is this function here. And notice it's a strictly positive function. All the positives align in time, and all the negatives align in time. Negative times a negative is a positive, and so we get a positive result here where the function had previously been negative. Okay, so that will give a finite result, which is what we want. We want some outcome here that will indicate how much of that cosine is present in f of t. Now, what happens when we multiply this cos 1 omega naught t by all the other terms? Well, I'm only going to show you one example here. I'm going to multiply cos 2 omega naught t, in other words, 2 cosine waveforms within the period, and I'm going to multiply that by cos 1 omega naught t, again following our formulation at the top there, and what you get for all of them are functions that look very much like this. They're quite, obviously if you have higher frequencies involved, we get even more waveforms, if you like, peaks rather, that fit in here. But they all yield functions which are as much positive as they are negative. You can see that positive peak cancels this negative peak. That negative peak cancels that positive peak. Likewise, negative, positive, positive, negative. So this function multiplied by that function, when we do a definite integral, gives 0. And exactly the same holds. Had I multiplied this by cos 3, or by sine of 1, or by sine of 2, sine of 3, all the way up to infinity, definite integral would yield a 0 result. Therefore, the only term that was left was the one that we're interested in, the coefficient for cos omega naught t. So I'm just stating there that I could have multiplied this by any of the other terms and I would have got a 0 result after the definite integral. So there I am emphasizing again that when I multiply cos by cos, which I'm assuming is present in f of t, there's my cosine squared, and we also must not forget to divide by the range of integration, and when we do that we end up with the average value of cosine squared, which is half, which is equal to a half basically if we just take cos of unit amplitude. Okay, so therefore to find any of the coefficients for the Fourier series, these are the Fourier analysis equations that we need to use. So we've got our real periodic function f of t, we multiply it by the term for which we wish to find the coefficient. So if we're trying to find the amount of cos n omega naught t that's present in f of t, then we multiply f of t by cos n omega naught t. Take the definite integral, divide by the range of integration, that will deliver an. And exactly the same procedure holds for the sine terms. Okay, so that factor of 2 then that we saw in the original definition, in our definition of the Fourier series. The reason for that is that if we do cos times cos, or indeed sine times sine, then the average value of that is only equal to a half. So imagine this had been a regular cosine of frequency 1, then it would have gone from 1 down to -1 up to +1. And so if you like, if that was what was present in the signal, then we'd only want a value of 1 coming out the other side. But the trouble is, if we do cos times cos and do that definite integral and divide by the range of integration to get the mean, we'd end up with a value of 1/2. Okay, and so that's why we need to multiply that by a factor of 2, because if it's got a unit amplitude and this integral only delivers half, we need to scale it up to compensate. So what we're saying is average value of cosine squared is 1/2, and so we need to account for that. So why is the average value of cosine squared 1/2? Well, hopefully it already is visibly very obvious. You can see that the function here is positive, and positive here and positive here. And if you like, there are these big missing gaps here. The values diminish down to 0 and back up to 1. And overall, you can see this is quite a symmetric looking function. In fact, it's given by this trigonometric identity, cos squared omega naught t is equal to a half plus half cos 2 omega naught t. And I hope you can begin to have some intuition there that this cosine squared waveform, you can see it's equal to a flat constant function of a half, okay, that's shown here, plus you can see this is actually a cosine waveform, and in fact two cosine waveforms that fit within the period, so therefore that corresponds to a frequency of 2. So even just cos squared itself could be written as a Fourier series, just as a side note. And the reason I'm stating that here is that it actually gives us a trigonometric identity, which also reveals that on definite integration, if we do a definite integral over that, then this cosine term is as much positive as negative. You can see cos 2 is positive, negative, negative, positive, and so on. That would give 0. And we're only left with this result here, just a value of a half. Okay, and so it's because of that average value of cosine squared being a half and the average value of sine squared being a half, that's why we've got these factors of 2 left in here to compensate for that. And it's just to do with how we defined our analysis equations for AN and BN. Just as a note, some people build in the factor of 2 with their definition of AN and BN, and you can do it that way. The reason I've done it this way is that I want this to directly link with the complex Fourier series, which will then ultimately lead us to the Fourier transform. And I want that to hold for all real functions, and I want to build it up without kind of changing definitions as we go. This way preserves continuity, if you like, in our description, building up to the Fourier transform. So that's why I've presented it in this particular form, and I hope now you can understand also why that factor of 2 is necessary. Okay, so here's the kind of grand finale of Fourier series. There is the Fourier series itself. That could be regarded as the synthesis equation. We're saying that we can synthesize or reconstruct or create the periodic function f of t by taking a constant term plus infinite number of cosines and an infinite number of sines, and then we get the quantities of the cosines using the analysis equations, which I'm showing here, and using, whether it's for AN or whether it's for BN, BN for the sines, AN for the cosines. And also to point out that this is valid whatever the period of our function f of t. So that's why we've got these omega naughts involved here, because otherwise we'd be limited to the case of requiring that the period of f of t be 2 pi. Which is a bit of a limited case, of course, and so these formulae are general. However, if you do have your function defined over a period of 2 pi, then have a look at this equation here. If t0, the fundamental period, if that's 2 pi, then 2 pi divided by 2 pi gives us a value of 1 here, and so all of these equations would simplify. The omega 0 would just be 1 everywhere. But I would encourage you to memorize these formulae for any arbitrary period t. And so as mentioned, these are called the analysis equations, and this, if you like, is the Fourier series or the synthesis. Okay, so in review then, we can represent any periodic signal by adding together sinusoidal basis functions. Those sines and cosines are often referred to as basis functions. And the reason this works, and we'll go into this in another video, is that because the sinusoidal functions are orthogonal to each other, which means that when we multiply one function by another function, if it's different, if it's one of the other terms, and if we do a definite integral, we will get a 0 result after integrating. And of course, when it latches on to the term of interest, in other words, when we're trying to find cos n omega naught t, when it gets multiplied by cos n omega naught t, we get a cosine squared, which will give a finite result after the definite integral, and so that allows us to recover the amount of that term present in f of t. Thanks for listening.